Has anyone ever wondered how an MRI works? How many of you have had to undergo an MRI? Or maybe some of you have no idea what an MRI even is. An MRI is magnetic resonance imaging. This is shown in Figure 1. It's a brilliant imaging technology that allows us to see inside the body with great detail as a cross-section. It also can allow or help doctors determine what is causing the pain inside of our bodies. As an MRI tech, the most common question that I get is, how does this thing work? Today, I will explain in simple terms just that. First, I'm going to tell you about some basic physics as it applies to MRI. Then I will explain what happens to the body when it's placed in a high-strength magnetic field, what happens to the protons in the body when a radio wave is generated and switched off, and finally, how all of these steps create an MRI picture. Okay, first I'm going to explain MRI physics basic physics as it applies to MRI. Atoms have a nucleus with protons and neutrons. The exception is the hydrogen atom. They only have one proton. Because of this, in this demonstration, I'm going to be using the terms hydrogen and proton synonymously. Okay, so mostly I'll be talking about the hydrogen atom. I'll be stating proton. A proton is a constantly moving electrical charge. It creates its own magnetic field, so it's constantly spinning in a circle. We use the hydrogen atom because it has an abundance in the body. Okay, first the patient is placed into a high field magnet, the MRI. Figure 2 shows a picture of this. Protons in the body begin to align themselves in the external magnetic field, and as I explained earlier, they have their own magnetic moment, so they are always spinning in a circle. Now, the speed at which the protons spin is dependent upon the strength of the magnetic field. The protons are aligning in two different energy levels. As shown here in Figure 3, there's a bar magnet with hydrogen atoms. They align in the direction of the external magnetic field, which is a parallel energy state, which as shown on Figure 3 on the right side. And they also align in the opposite direction of the external magnetic field, which is an anti-parallel energy state, which is on the left side of Figure 3. The preferred energy level is the one that takes less energy, the parallel energy state. A good analogy of this would be to think about when you walk around on the ground with your feet. This obviously takes, a minimal amount of energy. This is the parallel state, as opposed to walking on the ground with your hands, which requires quite a bit more energy. This is the anti-parallel energy state. A radio wave is then applied to the patient. See Figure 4. The purpose of this is to disturb or throw off the protons from alignment in the parallel state with the external magnetic field. They are already spinning. The radio wave makes them wobble. When it hits them, it makes them wobble. The radio wave must be applied at the same frequency, or in other words, moving at the exact same speed as the protons. This is important because this is what causes the resonance. The radio wave is then turned off, restoring protons to their peaceful states. The body acts as an antenna and emits a signal. A high-tech computer receives a signal from the body. It separates all the different signals out and then creates an MRI image. This is shown in Figure 5. There's an MRI image of the ankle and the knee. In conclusion, an MRI is a diagnostic tool that images the body in cross sections. For those of you who have had an MRI or may have to have one in the future, I hope this lessens your anxiety about this type of exam. The physics that I explained were very basic and only as it applied to MRI. The patient's body is placed in a magnetic field. Protons in the body line up. A radio wave is applied and then turned off. The patient acts as an antenna. A signal is transmitted and received. The signals are deciphered and separated by a high-tech computer, thus creating an image. Thank you.